So I guess we can start now. We are pleased to have Sourbh Bhadane here. So Sourbh did his BTech and MTech in electrical engineering from the Indian Institute of Technology, Madras, and then his PhD from Cornell. Currently, he is a postdoc at the University of Amsterdam. He has previously worked on information theoretically understanding of machine learning systems, and his current research interests are more towards causality. And today we'll learn about causality from him. So over to you, Sourbh.
Sure. Hi, thanks for the kind introduction. This is a paper that appeared in AI Stats last year. It's on the sample complexity of distinguishing cause from effect, and it's joint work with Jaydev Acharya and Sir Anand Kandasamy from Cornell, Arnab from NUS, and Zitang from Google Research. So let me start off with an example that may or may not be familiar, but it's quite a canonical causal inference example. So back in the 1950s, because of concern over growing lung cancer cases, these researchers, Doll and Hill, they published this landmark study, basically finding an association between smoking and lung cancer. So based on this and on follow-ups, the British Medical Research Council in 1957 said that, well, smoking causes lung cancer, and there was this whole public health campaign. Fisher, who was probably one of the most influential and prominent statisticians of that time, objected to this, saying that, well, you've just pointed out a correlation, and he said that maybe there's some other reason or some other what we call hidden confounder, that's, say, a gene that's increasing disposition to both smoking and cancer. So this problem of distinguishing between cause and effect is probably a very fundamental problem in causal inference. So there's this Reichenbach's common cause principle that posits that anytime you see correlation between two random variables x and y, then either x causes y or y causes x, or there is a hidden variable u that's probably causing both x and y. So now there are multiple ways to model causal relationships. We'll work in this semantic framework of structural causal models. Specifically, so here's the way we define it. If x causes y, then y is a deterministic function of x and some exogenous noise random variable ny. And this noise random variable is independent of x. So, and if y causes x, then it's the similar relationships in the reverse direction. So if y causes x, then y is generated by some exogenous noise, and x is a deterministic function of y and some independent exogenous noise. If it's the third case, which is if there's a hidden confounder confounding between x and y, then both x and y are deterministic functions of u, this hidden confounder, and independent noise nx and ny respectively, right? And here, I guess I've forgotten to write it down, but nx, the exogenous random noise for x, y, and u are also independent. So in this setting, an intervention corresponds to fixing the value of x to a realization x, right? And you could think of this as in vaccine trials having two different groups, control group and a treatment group. So in the treatment group, you fix that you're going to give the treatment to this particular group. And in the control group, you fix that you're not going to give the treatment to that, right? So yeah, this is the whole structural causal model for these two variables and the concept of intervention. So it is well known that without assumptions, if you just focus on observational data, and by that I mean samples from the joint distribution of X and Y, then just based on this observational data, it's impossible to distinguish between these three causal models. So it's impossible to distinguish between cause and effect just based on observational data and without making any assumptions. So, and the reason for this is that you could have a joint distribution that all the three causal models generate, like the same joint distribution generated by all these three causal models. So because most of the work in this area has focused on analyzing how to distinguish between cause and effect in the absence of any interventions. There's like a huge body of work on this problem, and I won't go through all of it, just suffices to say that there's like an entire book that completely focused on these methods that use only observational data. Now, if you use observational data, you also have to make certain assumptions, and those assumptions may or may not be testable. So yeah, most prior work on this problem has focused on just inferring from observational data. However, in some cases, you do have access to interventional data, and that's precisely the setting that we'll focus on. So if you're allowed to sample from these interventional distributions, that means the distributions that you get after you intervene on some variable. We are basically interested in how many intervention samples are needed, because perhaps these interventions are quite costly to implement. And we are also interested in finite sample analysis of this entire system. And basically, we're trying to find out what's the trade-off between the number of intervention samples and observational samples. So these are the central questions that we'll be focused on.
One question.
Yeah.
Yeah. So this intervention thing, is it the same thing as conditioning? Like interventional distribution is the same as conditional distribution, or is it something different?
Yeah, it's a bit different. I think that'll be more clearer ahead, but in a nutshell, conditioning is also observational in the sense that you can get the conditional distribution from the joint distribution. Intervention is fixing the value by force, right? So for example, in these control and treatment groups, we fix the values that they are not going to get the treatment or they are going to get the treatment. So yeah, but this will also be clearer ahead.
Okay, thanks.
Okay. So let's dive into the problem setup. So as we said, we are going to only focus on two random variables, X and Y, and these are discrete random variables over a domain of support size K. And here is this notion of correlation that we are going to use. So these two random variables X and Y are said to be TV correlated if they are intuitively, if they are far from being independent, right? And the precise definition is as given here. It's the total variation distance between the joint distribution over the random variables and the product of marginals where they are independent. And the total variation distance is basically half of the L1 distance, right? So another interpretation of this particular quantity, this total variation correlation, is that it's the expected total variation distance between the conditional and the marginal, right? So for these two random
mutual information.
Say that again.
More or less the same as mutual information, is it not?
Yeah, if this total variation would be KL divergence, then this would just be mutual information between X and Y.
We can relate them by inequalities. So
Yes,
we could argue for the information quantity as well.
Yeah, fair. Right. So we assume that the strength of correlation is at least some epsilon parameter, right? So all our results are going to be in terms of these two parameters, the domain size K and this strength of this TV correlation epsilon, right? So we'll start defining the precise problem that we are interested in, which we call causal structure identification. And we assume two forms of sample access. One is, as we said, observational samples, which are samples from the joint distribution over X and Y. And the other is interventional samples, which are samples from this interventional distribution where, as we mentioned previously, this operation is different from conditioning. Here we say that we are fixing this realization capital X to this, fixing the random variable capital X to this realization small x, right? And we are getting samples from this pxy. You could also intervene on y and get samples from x, right? So these are the two forms of sample access.
How is
And
this really different from conditioning? You are conditioning on some event, are you not?
you're not conditioning because you're not sort of observing from data of the joint distribution, right? Conditioning would mean observing, like, what is the distribution of y if you observe x is equal to x. So here you're doing something slightly different. You're fixing the value of capital X to be this small x, and then you're observing what the change is in y.
Sorry, it's still lost on me. Does anybody else understand it?
So I can give, like, a practical example would be, let's say you collect, like, let's go back to the smoking and lung cancer case, right? Let's say you collect data just by observing people all over all across the town, right? You get data from people who are smoking and people who are not smoking, right? So this is all observational data. Now, suppose you actually wanted to go ahead and find out whether smoking causes lung cancer. The way to do that would be to kind of have two random groups, where for one group you force them to smoke, and for the other group you force them to not smoke, and then measure effects. So this act of forcing this particular random variable to be a realization, that is an intervention.
Yeah,
So
but even if you do that, won't the, like, let's say you are only observing samples from the set that you are forcing to smoke, even won't that distribution, like, won't the data samples be generated from the conditional distribution of p y given x equals to smoking?
That's only if smoking causes lung cancer, right? Let's say lung cancer causes smoking. Then if you make any intervention on smoking, the distribution of lung cancer would not change. And this again, this is a point that we'll make as we go ahead. But
Is it possible to write a definition of this probability distribution in question?
Sorry, could you say that again?
Is it possible to write a definition of this PY condition on do x equals x?
Yeah, we could do that.
Can we now?
I think that's also there in a future slide. So I'll.
If it's down the road, let's not stop for that.
Sounds good. Yeah. All right. So, yeah. So this is the causal structure identification problem. Precisely is stated as follows. So if you have an SCM over two observable random variables x and y, that's supported over this domain of size k, and that satisfies that the strength of correlation is at least epsilon. We want to find basically an algorithm that identifies the correct causal structure given M0 and M0 observational samples and MI intervention samples, and it identifies the correct causal structure with some constant probability, right? And we are interested in this trade-off between the number of observational samples and the number of intervention samples.
So I have a quick question before we move on. So is the difference between the conditional and what you're doing here just that, like, when we sample from the joint distribution, you can say that I'm only going to look at those which, let's say, only those people who smoke, and then that gives me the, and then look at what distribution on Y there is,
yeah,
and that is the condition. But if you force people to smoke and then you get a distribution on Y, then that is your intervention.
Yeah, that's
Is that
what yeah, that's the difference. Like, so in that case, when I'm forcing some group to smoke, then I may like the distribution may or may not be the condition, right? If what I'm forcing actually has a causal effect on what I'm measuring, then sure, then it's a conditional. But if there is no causal effect, then me intervening or forcing this treatment would not make any difference in the intervention.
But isn't that the case even if they are like, so if there is no causal structure and they just turn out to be independent, right?
Yeah, even then, if you intervene, then the distribution would be the marginal distribution. So so maybe since this is like an important concept, I can illustrate it using these SCMs here. So over here, let's say that this is the first figure is the correct causal model. Then intervening on X, sure, would give you that the interventional distribution of Y is the conditional distribution. But if I intervene on Y, you can see that if I fix Y to be some value, then the distribution of X wouldn't change, right? The distribution of X would just be the marginal distribution. So that's the difference between conditioning and intervening. The conditional distribution of X given Y is clearly defined, and that's not the marginal. But here, the interventional distribution, when we intervene on Y, that is just the marginal of X.
I see. Okay, I see. Thank you.
Yeah. So yeah, this is overall sort of the trade-off graph that we obtain, and all the X and Y, sorry, the X-axis and the Y-axis also, those are interpreted as order. So on the X-axis, we have the number of observational distributions. On Y, we have the number of interventional samples. And you can see that there are a few phase transitions in this graph. But as the number of observation samples increases, naturally the number of intervention samples keeps decreasing. And today I'll just focus on this regime here because that's kind of the most interesting regime where we have sublinear number of observational samples and also sublinear number of intervention samples. So this is sublinear in terms of the domain size K. So less than K, both observational and intervention samples. By the way, the bold lines indicate that the trade-offs that our algorithm gives is optimal. And this particular region for that, we still don't have tight lower bounds. But all right. So let's say that we wanted to test if X causes Y or not, right? So as we've probably tried to understand this meaning of intervention just now, this might be more clearer. So if X causes Y, then for every X, for every symbol, the interventional distribution of Y is just the conditional distribution, right? And the reason for that is that our structural causal model, if in this X causes Y case, becomes that X is just fixed to this symbol small x, and capital Y, which is the deterministic function of this X and some exogenous noise, right? So this distribution depends on X, and it's exactly the conditional distribution. However, if X doesn't cause Y, then for every symbol, the interventional distribution of Y, if you intervene on X, that's just the marginal, right? So you could take both cases. One case is Y causes X. So in that, an intervention on X wouldn't change the distribution of Y. And this is also given by the structural causal model that we saw, where the distribution of Y is just some exogenous noise and capital X is intervened on. So therefore it's fixed to X. And the case where there is a hidden confounder, in that case also, if you intervene on X, then as we said before, both X and Y were functions of deterministic functions of U and some exogenous noise. So in this case, because of the intervention, capital X is fixed to small x. And because of the intervention, there is no difference in the generation of y. So that's why the interventional distribution is just the marginal distribution of y. So this observation basically makes our algorithm quite easy to state, which is that if I want to test between these two cases, x causes y and x doesn't cause y, then it's sufficient to find a symbol to intervene on such that the conditional and the marginal are far apart in TV distance. And then I would test using samples whether the interventional distribution is close to the margin using observational and interventional samples, right? So these are basically the two subtasks that I'm going to focus on. I'm going to focus on the second subtask first. So this second subtask of testing closeness between two distributions is quite well studied. So here you have IID samples from two unknown distributions. And so you have NP samples from one distribution and NQ samples from the other. And the question you ask is whether these two distributions are the same, or they are away, or they are like alpha away in TV distance, right? So you accept if these two distributions are equal, and you reject if the TV distance between these two distributions is greater or equal alpha, right? And these two distributions are unknown, of course. So, and you want to do this with high probability, at least some constant probability. So this is a well-studied problem, and there's a long line of work that exactly pinpoints the optimal sample complexity of this problem. So we know that there is a computationally efficient closeness tester such that the trade-off is given by this particular expression. So one thing to note here is that as the TV distance increases, this problem gets easier to solve, right? That's kind of natural that if two distributions are far apart, then you need fewer samples, right? And here you can see that even if I have infinite number of samples from one distribution, which means effectively that even if I learn that distribution completely, I still require this root k over alpha square number of samples to test if this Q distribution is equal to this kind of known distribution, or is it far away by epsilon, right? So yeah, so this is the trade-off for closeness testing. And now let's see how it appears in our case. So in our case, we remember that we want to test between the marginal distribution and this interventional distribution. This interventional distribution, as we said, if x causes y, it's the conditional distribution, and if x doesn't cause y, then it is just the marginal distribution, right? So in our case, again, the sample complexity, that is the number of interventional samples required in terms of the number of observational samples, is given by the same expression that we saw before, right? But there's a catch which I'll come to in the like in a second. But firstly, note that this number of interventional samples and this expression kind of looks similar to what I have already shown before, right? The trade-off that I showed before, that kind of mimics this expression here. However, the difference is that this alpha now depends on x, right? The trade-off that I showed here, that depended on this strength of correlation, on this strength of TV correlation epsilon. Whereas here, I don't have any of that. I have this alpha, which is dependent on the symbol x that I intervene on, right? And this alpha can be at most the TV distance between the conditional distribution and the marginal distribution, right? So then our second problem is where to intervene, right? So this is the first subpart of our algorithm. Remember this algorithm here. We wanted to find some symbol to intervene on and then test if the interventional distribution is close to the marginal distribution or not. So we've kind of looked at this second subpart. And now I'd like to move on to finding which symbol to intervene on. right? So, and I'll kind of motivate this from a toy example. So consider that you know that the TV correlation is around epsilon. And let's say that I have two cases. Either a symbol is completely uninformative because its TV distance between the conditional distribution and the marginal is 0, or it's informative, meaning that the conditional distribution, the TV distance between the conditional and the marginal is greater than epsilon. Right, so we would like to sample these informative symbols, and because of this TV correlation definition, we know that the probability of sampling this informative symbol is epsilon by tau, right? And we also know that if given this particular condition, we know that the number of samples required to test between the interventional and the marginal is given by this particular expression, right? So in essence, what this means is that if tau is large, then sure, the closeness testing problem is easier, but the probability of sampling this informative symbol goes down, right? It's rarer to find this informative symbol. So there is some tension between, there's like a trade-off between finding this informative sample and the ease of closeness testing. So specifically, here's again the definition of this TV correlation in terms of this expected TV distance between the conditional and the margin, and that's greater or equal epsilon. So what this means is that on average, these conditional and marginals are far apart. So if that's true, if on average it's greater than epsilon, then of course there exists at least one symbol where the TV distance between the conditional and the marginal is at least epsilon, right? So one naive attempt would be to intervene on every symbol and check and run the closeness testing, basically. But this would give us a super linear sample complexity, right? Because whatever sample complexity we saw previously, that will get multiplied by k, right? A better attempt is to observe this inequality here. And this is not very, I'll quickly prove this in the next slide, but it basically means that if this expectation is greater or equal epsilon, then by law of total probability, the probability that this probability of finding some symbol that is epsilon by 2 far is at least epsilon by 2, right? So what this means, what this probability statement means statistically, is that if I draw order 1 over epsilon samples from this marginal over X and intervene on them, then I'm done, right? So instead of my sample complexity being multiplied by K, I can now test just using order 1 over epsilon sample. So my sample complexity would be whatever we saw previously multiplied by 1 over epsilon. And quickly, let's kind of look at why this why the expectation lower bound means the probability lower bound. It's just law of total probability. I can decompose this Q of X function, which is the TV distance between the conditional at this realization X and the marginal, right? And if this is greater than or equal epsilon, then I know that this second term is at most epsilon by 2 because this probability is bounded by 1. And because of the conditioning, this expectation is also bounded by epsilon by 2, right? So then this follows. And as we said, statistically, that just gives us like a 1 over epsilon multiplicative factor in our sample complexity. The question is, can we do better than this? Can we completely remove this 1 over epsilon extra multiplicative factor? And it turns out that you can. And for this, I'm going to introduce this slightly lesser known trick by Levin. So this is like his work investment strategy. So I'm going to abstract out the problem a bit, but I'll definitely draw some parallels with whatever we are considering. So let's say that you have a space X and there's some probability distribution over it. And you have, so you think of this as the marginal over X, right? You're sampling points and you don't know which one to intervene on, right? then consider a function, a quality function defined on this space X. So this quality function maps points in X to 0, 1, the interval 0, 1. And you can think of this as the TV distance between the conditional and the margin. And importantly, we don't know what Q is, right? We don't know this TV distance, right? And all we know about the Q function is that in expectation, it's at least epsilon. So this is similar to our strength of TV correlation being at least epsilon. And finally, we have this work function, which is inversely proportional to the quality. And we should think of this as the number of intervention samples required for closeness testing for this particular symbol small x, right? So this is inversely proportional to the TV distance between the conditional and the marginal, as we saw, those alpha squares and alpha raised to 4/3 and so on. And our task is to minimize the total work to utilize one point fully, right? So we have this unknown quality function and we have this work function, and we want to minimize this particular quantity, the total work, to utilize one point fully. And what this means in our setting is that we want to basically find one X so that we can reliably do closeness testing on it, such that this TV distance between the conditional and marginals is high enough, right? So if this is clear, then I'm going to sort of draw a parallel to the previous sort of better attempt, right? We said that the expected quality is greater or equal epsilon, and that implied that this quality being greater than epsilon by 2 is at least epsilon by 2. So the total work that's invested in this is, because we are sampling 1 over epsilon samples, it's order 1 over epsilon multiplied by how much work we are investing, which is order 1 over epsilon again. So this is order 1 over epsilon square because of that. And now let's see our better strategy, right? So what Levin proposes is that if you take your domain Q, right? Remember that Q is the quality function maps points to the interval 0, 1. So what Levin proposes is that you divide the range of Q into log 1 over epsilon geometric intervals, right? So here L is log 1 over epsilon approximately. And I'm showing you only, so this particular schematic is basically showing you only the left half, right? And it's divided into these L geometric intervals. And Levin says that instead of making this one weak statement, one weak probability statement, you make L number of stronger statements that out of which at least one of that statement is true, right? So, and Levin's claim is that it turns out that testing these L stronger statements is more efficient than testing this one weak probability statement, right? So in particular, to see why I'm calling these weak and strong, you could let J here be equal to L, right? If J is equal to L, then it's basically this particular, this first interval. And you can see that the probability that Q of X being greater than, so 2 power minus L is like approximately epsilon by 4. And the probability statement here on the right-hand side, this particular quantity, is like almost a constant, right? Whereas this implication of the TV correlation being at least epsilon, the probability statement implication is that this is at least epsilon by 2, right? So the probability that Q of X being like epsilon by 2, greater than epsilon by 2, is at least epsilon by 2. So this epsilon by 2 is like a fraction, constant fraction here. So that's the reason this is like a stronger probability statement. But of course, it's not true. It need not be true. There could, like, at least one probability statement among these is true. That's all this is saying, right? So let's see how testing at least one of testing all of these strong probability statements becomes more efficient than testing this one weak statement. And remember that the total work required to test, total work for this strategy is order 1 over epsilon square. Right, so you have log 1 over epsilon candidate guesses for this Q of X, right? And our strategy is basically the same. If you sample the inverse number of quantity, inverse number of points for this particular jth sample, and you invest like 1 over this much work in each of these samples. So L over 2 power j epsilon points you would sample for the jth guess, and for that you would invest basically 1 over the quality, order 2 power j work. So you see that the total work, if you sum over all these L guesses, is L square over epsilon, and L is like log 1 over epsilon. So if I ignore these log factors, then it's O tilde 1 over epsilon as opposed to order 1 over epsilon square that we saw before, right? So this completes our algorithm basically, which is we defined the range of 0 to 1 between these L geometric intervals, and for every interval you sample these many symbols from the distribution of X and you intervene, and for each intervened symbol you do this closeness testing. And so it turns out that the alpha that we had before, that can be replaced by this epsilon, and we lose like some log factor in the sample complexity, right? So that's basically the trade-off, the sample complexity trade-off for the algorithm. And now we'd like to see if this is optimal or not. And again, it's sort of like a reduction to the lower bounds or the hardness results of closeness testing, except that there's slightly like more complications. So I'll move on to that. Up till now, if anyone has questions, I can take those for like the algorithm part. All right.
So your work
Yeah.
invest was the closeness testing work?
No, work investment is like this result by 11. So that's sort of different than closeness testing technically. It's just like some abstract problem for which it's like some investment problem for which Levin proposed this solution. And we find that it's useful to apply that in this finding intervention problem. So, yeah. All right, so I'll move on to the hardness results. So remember that we said that there is a computationally efficient tester for this asymmetric closeness testing problem. There is also a matching lower bound that says that any computationally efficient tester that draws these many samples from both the distributions requires the same expression. Requires the same expression of number of samples. So the proof is to just construct like hard instances of these distributions P and Q, right?
How do you mean any computationally efficient tester? Can you just say any tester, never mind computationally efficient or not?
I think you could say that any tester is also fine. This computationally efficient tester is not a restriction.
Right.
Right. So the proof basically involves coming up with these two instances of distributions P and Q. And the idea here is that you construct these hard instances such that there are two subsets of elements. One is what we call heavy elements, and the other is light elements. And the difference between P and Q is only in these light elements, right? So these light elements basically occupy a large chunk of the domain, like half of the domain. By the way, I think these constants are off. It should be like 1 over 8K and not 1 over 4K. But anyway, the point is that these light elements occupy most of the domain and these heavy elements occupy few of the domain. So the idea is that when you see samples from P and Q, you're mostly seeing the heavy elements, but you're not seeing the light elements that much. But the light elements are the ones that are causing like a difference between P and Q. And so you need to sample an appropriate number of samples to really see the difference between these two distributions, right? So that's the whole idea. And this is like the specific exact construction of these distributions. And then the rest of the technical work is to show that these distributions indeed can't be distinguished, right? So in the case of, so I won't go into like the technicalities of this, but I'd like to present briefly kind of what's different in the causal setting, right? So in the causal setting, the adversary has multiple distributions, even in a bivariate system, right? Instead of constructing hard instances of distributions, we are now interested in constructing hard instances of these structural causal models, right? So, and this is for the case of the sublinear number of observations. This is our lower bound, which is essentially matching the upper bound that I had shown before, up to log factors. So let's sort of go through one instance of constructing these lower bounds. So consider this causal model where X is distributed as Bernoulli half, and the conditional distributions are Q and Q minus. And these are the definitions of Q and Q minus here, basically. We don't really use P, but Q and Q minus are, you can kind of draw a parallel between what we saw earlier and Q and Q minus here. So the distribution of Y is actually P here, right? So the adversary has not just two distributions in the case of like closeness testing, but it now has four distributions, which is the conditional distributions, P y given x equals 0, y given x equals 1, and these interventional distributions, right? So essentially, when the previous task was just to distinguish between P and P and P and Q, now the task is to distinguish between Q and Q minus, P and P, right, in this case, and Q, Q minus, and Q and Q minus, right? So when this marginal distribution, so when these interventional distributions are the marginal, so that time it's P and P, and when these interventional distributions are the conditional, that time it's Q and Q minus. So
Your hypothesis between the two tuples, that's what you mean? Like
yeah,
the
yeah.
two four tuples.
Right.
I see.
Yeah, you don't want to distinguish between these four tuples. So, so yeah, in the paper we extend basically this setting where you have just two distributions, where you have these two pairs to like these four tuples. So that's like the hardness results that we have. So finally, I'd like to kind of conclude by looking at this, final piece of the puzzle that I like to call it. So here we said that in this region, we don't have tight lower bounds, right? So to kind of give a reason as to why we don't have that, let me recall the algorithm, which is that we want to find a symbol to intervene such that these conditional marginals are far apart. And we are testing if the interventional distribution is close to the marginal using these observational and intervention samples. Now, I'm kind of intentionally missing out one thing, which is that I could test if this conditional distribution is close to the conditional, if I could test if this interventional distribution is close to the conditional distribution also. I don't necessarily need to test if it's close to the marginal distribution, except that when I'm drawing samples from a joint distribution, I definitely have way more samples from the marginal distribution. However, our claim is that in this regime, when you have sufficient number of observational samples, these conditional samples start becoming more useful. So technically, this second part need not just be a closeness testing problem. It's actually a classification problem where you want to test if this interventional distribution is close to the marginal distribution or the conditional distribution, given that we know that it's one of them because of the setting that we are in. So this is a classification problem. There has been very recent work studying this classification problem, but most of that is like in the equal sample setting, right? So in the unequal sample setting, it's still to be looked at, and hopefully that kind of closes this lower bound gap. So to conclude, I'll basically summarize our contributions. One was that we introduced this notion of correlation that can be used as a parameter in like a finite sample analysis of these bivariate causal systems. We proposed like these near tight trade-offs between observational and interventional samples, and also came up with these hardness results for causal models, which was not done before. As future work, I think we would like to smoothen these phase transitions and kind of move ahead from these bivariate SCMs. So yeah, that's where I'd like to end and take questions if there are any.
Thanks, Saurabh. Any questions from the audience? If not, maybe I have one question. Can you go back to the figure in the last slide? Yeah.
This
So you said that in the middle section the lower bound is not tight because of too many observational samples. This becomes a classification problem. But then again, in the later section, you again have a place where both of these things meet up. So
Yeah.
happens in that region.
So in this region, it's basically that you have so many observational samples that all the distributions that you care about, those are all effectively, the distributions very well, right? So it becomes like a density estimation problem. And so for that, it's just 1 over epsilon square.
I see.
And so so that 1 over epsilon square, which is the number of interventional samples, is that algorithm like just looking at these distributions and comparing it? Is that all you need to do?
Yeah, you just look at the interventional samples and it's kind of like just hypothesis testing at this point. Yeah. So you have two hypotheses and the distributions entirely, the marginal distribution, and the conditional distribution. So, and that they are 1 over epsilon apart. So, I mean, that they're epsilon distance apart. So that's why it's just 1 over epsilon square.
I see.
So yeah, that's just like, this likelihood testing.
Okay, thanks.
Thank you.
Right.
Yeah, thanks, Saurabh. Very nice meeting with you, and hopefully we'll have your time. Thank you.
Yeah,
It was
thanks.
very.
Right. Have a nice day.
Okay, bye. See you.